tell us about what we found at Kentland crater. And I think we figured out how large it is finally. So yeah. So Brian, yeah.
All right, so I'm good. Thanks, Doug. Yeah, this Doug kind of alluded to on this one. This has been a pretty full circle like trip with this data. You know, Christoph came to Doug's lab, helped us collect the data. He came on a Fulbright grant, and then now I'm back with them on Fulbright processing the same data. So it's pretty nice little turnaround with that. So, but first I'd like, there we go. So I want to discuss the purpose of us doing this survey was to just basically understand this impact structure's geometry, as well as the seismic physical properties, such as the damage, porosity, etc. As Doug had said in this intro, it's not really fully known the size of the crater. It's been quoted at 12.5 to 13 kilometers, but it's because a loosely used term of there's a disturbed area that extends that far, but I don't know if they're saying it's the crater or not. It hasn't really been seen. But with that, we have seismic wave speeds are very sensitive to the damage, porosity, and density of it. And the example I'm using today is just for Kentland crater. And to address the elephant in the room image of the gravity map of the moon, the reason it's there is the impact structures commonly show pronounced gravity negative anomalies due to the occurrence of low density breccias, rock fracturing, the replacement of the ejected material by post-impact young sediments. And here on the moon, let's see, you see these blue circles. These are all low velocity or gravity negative anomalies. And it's weird with Kentland crater because we actually see a gravity positive anomaly. So it's quite different than what we're used to seeing on it. And talking about impact craters, I just wanted to go over the brief formations of them. So that way we can all be on the same page and then go on from there about it. So I'll be going from top to bottom on these images discussing it, but the smallest impact craters we have are called simple craters because they have a simple bowl-like shape. And these craters are excavated when an asteroid, which is the most common impact type on Earth, or a comet hits the surface. The average velocity speed for the asteroid on hitting Earth is about 18 kilometers a second, just to give you a rough idea of how powerful and fast it's coming in at. And a shock wave radiates out. It hits it, sends a shock wave through the Earth, and then it actually sends a shock wave back through the projectile, where it hits the back surface of the projectile and then back down forward through the planet's crust behind the shock wave. So that's the rare refraction wave, and that then radiates through it. The crater begins to grow when the object penetrates the surface and the shock waves compress the planet's crust downwards. And the main phase of the excavation occurs after both the shock wave and rare refraction waves pass through the crust. The two waves leave behind a little residual particle velocity that causes the material in the crust to flow. Initially, it's downward, but then it moves outward and upward, producing the ejecta curtain that's coming out. And that grows as the crater grows, as you can see. And the impact ejecta falls out along the crater walls. But the rocks that float along the crater walls but were not ejected, they slump towards the bottom of the crater, which gives you this breccia lens. So you get this nice bowl-shaped fractured floor with breccia lens. So simple crater. What we're dealing with here, more so in Kentland, is what's called a complex crater, and same initial stages, compact compression going out. But this one is a larger impactor, hits and sends the shock wave through it, radiates through the crust and causes it to flow. But so initially the flow of rocks move downward and outward from the point of impact. But then it sweeps outward and upward, creating the bowl-shaped cavity that grows deeper and wider. The shock wave compresses the crust, pushing it downward, but when the rare refraction wave passes through, it actually causes the crust to rebound, which is what you're getting, this little central peak uplift rebound. And it rapidly rises, forming that peak, and the walls of these craters it's very deep, and it can only withstand so much, it can only be so deep given the planet's gravity. So it causes them to collapse and slump down inward along the faults, producing this modification zone. And there's so much impact. The kinetic energy with these impacts, it actually gives you a melt sheet across it. It melts the surface. And so this is what idealized complex crater looks like. However, with Kentland, we're dealing with something a little bit different, harder to define. That's why what we're going at with our things is this eroded complex crater. Because before, if you picture the image, you can define it as, hey, there's a nice crater rim that you can see and well define where it's uplifted and say, this is the diameter of the crater. However, due to all the erosion from the glaciers, what, 10, 12,000 years ago, it's estimated the top 300 plus meters have been eroded off. So we're left with this shaved surface where using seismics to see the outer faulting to determine this is now the apparent diameter of the crater. So we're not going to have like a true real diameter because that has been wiped away from us. And to go into a little bit more morphology of impact craters, we have that transition from simple to complex. It's approximately 3 kilometers in diameter on Earth. However, it varies on the planetary's gravity as well as what type of material is the impact of hitting. So on Earth, it's about 2 kilometers in diameter for sedimentary rocks and 4 kilometers in diameter for crystalline rocks. So that gives you the adjustment on there. And these are just some examples of a simple crater and a complex crater. This is one taken from the HiRISE craft for Mars of a simple crater, and this is a complex crater from the moon, where you see the central uplifted area as the central peak, and that is what is exposed at the Kentland quarry that they're mining for limestone. And this is just showing the pressure field because the shatter cones are present at Kentland. So I wanted to show this because that forms and pressures, 2 to 20, 30 gigapascals is form getting those pressures when you're dealing with an impactor or a nuclear bomb. So just a quick overview of Kentland crater. It is an impact structure located in Newton County, Indiana. Its area just flatline Paleozoic rocks. It's a deeply exposed in a quarry mined for limestone. This is an old image of the quarry I like because everything is just flat. It was discovered in the 1880s, I think. 2 farmers were quarrying for crushed rock. They ended up finding the shattered or the uplifted and the evidence of an impact, but it wasn't until later when it was linked with the shatter cones. So it was the first location that actually linked the shatter cones, the hypervelocity impacts. And you can see over here, this just bedrock unit map of Indiana. We have Kentland over here, this little circular depression where it's going to be impossible for you guys to see, but there's a mix of these ones because of the impact. It brought up different layers and whatnot. So going with, and here's just a fun little EAPS image that they did on one of the classes with where Jay Malash ran to both sides for the panoramic picture, but it's just showing the central peak where you see these, something's not right. Rocks are going vertically rather than horizontally. So they knew something was up. So this was just a nice shot I wanted to share with what we're actually looking at the central peak. The Rogers group is actively mining it. So we actually get to be inside of it, which is a plus for the scientific realm. Going on our seismic profile on this image, I'll try to use my laser. These are small dots, but we had a big area. This is the quarry right here, this white area. We have these things in red. These red dots are called, I call them permanent smart solos. What we did is we placed these smart solos out and left them there during the duration of our survey. These temporary smart solos we used to cut the profile to kind of quasi 3D when we rolled. So we planted these 2, shot the line. Once we rolled and we were more coming down here, we picked these up and put them down here. And so they were just temporary, and we recorded all that. Yeah, and our receivers, we went down this road Didn't get as far as we wanted to. Our goal was to kind of cross this river aspect of it, but it had some mechanical issues with the vibe. But yeah, we had 49 of those smart solo nodes that were permanent, and then we used about 53 for the cross lines in total. And it says on here we had 4 to 8 meter spacing. We had 8 meter spacing on our shots and receivers, or on our shot points at the very beginning and the very end, but we had 4 meter spacing intervals for the rest of it due to the roll. So that was really nice. And yeah, we acquired 5.3 kilometers of data of it, and seen some interesting results from that so far. I ran this tomography off of this RAFRAC program that we had back in the States. And one thing I want to note, I told you 5.3, but this x-axis you can see doesn't go, it gets closer to 5. Our license key that we had was just the general academic one, so I couldn't incorporate more than 1,000 shot points in it at once, and we had 1,298. So I just cut it down to every other shot point and was able to get this profile. This z-axis is in meters, and these are meters per second. But take this image. I guess I could have done it on here, but if you squish it down and elongate it, is what we're looking at. So it's not as dramatic as an increase. Didn't know if this was an artifact or not looking at it, but seeing this result and then seeing preliminary results, and when I ran my velocity models here from scratch again on using Geotomo, I'm getting very similar results on it. So it's really nice looking at that, where this is the start of the profile going down the line, and we're seeing something with this low velocity zone and some random higher pockets. So it's quite an interesting image so far, I like. And I wanted to include a cross section of Kentland crater, as many probably have struggled in the past with in there. I took it from this paper Laney and Van Schmoes did in 1978. It's one of the most comprehensive ones I've seen that actually give me depths. They're not cited where he got them, but he did it. So I'm using it because it kind of matches up with my data quite well. And we have a basement depth of about 1.68 kilometers. This is wrong. It's a minimum of about 300. Could be more, really hard to tell. But one of the things that we're looking at here is this is just a legend to kind of describe what these rock layers are that he named them. The Shakopee dolomite is the oldest rock that is exposed at the surface in the Kentland crater. So that has been uplifted about 600 meters to be at the surface present. That is what we're dealing with on this one. And so I wanted to kind of place these layers and what I can get out in the image that we ended up producing. And it's an estimation on his diameter cutoff, but going from this, just to give you the bedrock layers, and created this image with, this is a Kirchhoff pre-stack depth migration. A couple things I want to highlight on this is I had to create a local coordinate system and apply a rotation matrix to have it horizontal. So our starting 0 is 1,000, and it pretty much ends at 6,000, which is not the full length of the profile, but I was playing with some things to, I basically gave it the parameters to say, hey, limit your offset to stuff within 250 meters of this to kind of enhance the signal to see it. And so it's not including anything on the outside yet. And this was also done using a constant velocity of 4,000 meters per second. So stuff is a little bit shifted down, but it's pretty nice because you see some nice reflectors, which in later images we'll see like pretty much match up where the basement rock is on them. And we have a lot of these different layers here. And hate to do this to you, Doug. I had a new result today. I didn't include it on this, but it was actually kind of cool. I ran a coherency migration to kind of play with the noise and see if it happened. It changed some things, but it actually highlighted what looked to be a pretty nice fault right in this area that was very vague, very hard to see on this image, but it's visible, and then it came out quite clear. So that's pretty nice. I'm kind of excited, but we're gonna run it again on the supercomputer and get a better result, and then we'll look at that when you're here. But then also up in this section, it kind of cleared out and made it look like there was a fault at this edge. So it was pretty nice to see. So we're getting somewhere with this. Again, this is just a pre-stack depth migration on it. And then this was with Vista. So yeah, I guess going back to this one, I have coded the velocity file I created to extend it all the way down. So that way it'll be done proper. This is just done with a constant velocity stack. Now in Vista, I took all the data and processed it through Vista as well that we have. This one, just an overview of it. I did a bottom mute to cut it at 1200 milliseconds because the data pretty much, as you see after 1000, is just, it's a lot of noise. There wasn't really anything in it. I didn't see any reflectors. But you see these layers, so that just even using a constant velocity of 4,000 meters a second, you're hitting that basement rock around the 840 millisecond mark. So we're at least seeing some stuff, which is nice. There is that dip down with these, so I don't really know if this, in the interpretation of it, Doug and I need to meet on and discuss, but it's quite interesting whether it's the extent of the transient crater diameter or not, which can play into the size. So it was quite interesting looking at that. And this is just a grayscale image I wanted to show. Some people like this to highlight them more, to kind of have that. But the main thing I wanted to do then, if you remember the tomography image that I showed you, I want to overlay it, and you see that it meets up quite nicely. Of it kind of flows with it as it goes with the different velocities. So at least I like it to where, you know, the data matches what I'm getting when I do the tomography and vice versa. So it's making sense that way for me. So that was a good result that I like seeing. But yeah, it's quite an interesting thing. And just like I think Ryan had said it yesterday, of this area is just really wonky with the seismic data to try to get done properly. So it's been a challenge, but fun to kind of see this for my first attempt on it. So it's pretty good. Then yeah, the conclusion on that one for Kentland, our goals going into it was to create that velocity tomographic inversion for the velocity structure. Not that we've done that already, and now we're in the phase of looking at these outer faults, cleaning up the data, and trying to figure that. So pretty much getting there with that, which is nice. And then future work involved around the Kentland areas, we can go more the petrophysics route, have the porosity mineralogy and whatnot in our lab. There's some core samples we can look at. Maybe we'll get funding to do some drilling ourselves, who knows. And then look at velocity and anisotropy on the rock samples in our lab, as well as we can conduct our own gravity survey throughout our seismic profile to kind of match everything up. And one thing that hasn't been touched yet really is analyzing the smart solar data set. So that's another thing that we have in the future to knock out on this one. So excited to see what comes from this to kind of better understand this, but it's making good progress on it for sure. So yeah, with that, I hope I didn't go too much over. Yeah, I can take any questions.